Friends, greetings again from Vidyavardhaka College of Engineering, Department of Civil Engineering. I am into my second lecture on foundation engineering, part of geotechnical engineering. So, if you just go back, the focus of this gate training is to crack the questions of gate 2022 papers. And hence, I did solve a few problems in the previous class pertaining to foundation engineering. In fact, gave some brief introduction also on foundation engineering. Of course, bearing capacity happens to be the most important aspect. I did cover some aspects of that. I'll continue further on the same. So we'll have foundation engineering, we'll have bearing capacity, and the focus will be on further bearing capacity, settlement, and later on pile foundation. I hope to cover these topics in the next 45 minutes. Well, friends, just recapitulating what we studied in the last lecture, most important thing from the point of view of design of foundations is to arrive at ultimate bearing capacity of soil. I showed you a number of failures, and these failures are purely because of lack of proper understanding of the soil. Assumed bearing capacity is lower than, rather higher than, the actual bearing capacity. Either, some critical condition has happened because of heavy rains or maybe earthquake, or you design it for something and put extra load. You say that, okay, 3 floors this building is taking, and you build another 2 floors. Naturally, provided bearing pressure is much more than the capacity, and that may lead to failure. Let's go back. The equation for finding bearing capacity, QF, ultimate bearing capacity, is given by C and C plus gamma D and Q plus zero point 0.5 gamma B and gamma, and all the terms you are familiar with. Remember, NC, NQ, and gamma, you call them as bearing capacity factors, which are purely dependent on the friction angle. Then you have cohesion, depth of foundation, width of foundation, and density to be taken into account. And this equation holds good for strip footings. In case the footing is different, of different shape, the coefficients behind NC, NQ, and gamma will have slightly different factors to be, multiplication factors to be considered. Let's go back to the problems of last gate. This was one of the problems. Okay, I read here. You have to check whether these statements are true or false. I take the first one, P. It says, while designing a shallow footing, please note, while designing a shallow footing in sandy soil, monsoon season is considered for critical design in terms of bearing capacity. Is it correct? Is it true or false? So you need to go back to the equation for bearing capacity. And this is the equation for bearing capacity. I have taken Terzigi's bearing capacity theory. Compared to the last equation, I have just added the effect of water table. So whatever you see here, RW1 and RW2, they form the coefficients which have to be taken into consideration due to the reduction in bearing capacity because of the presence of groundwater table close to the building, close to the foundation. If the groundwater table is far off, at great depth below the bottom of the foundation, RW1 equal to RW2 will be equal to 1. But when the groundwater table is close to the surface, these values of RW1 and RW2 will be less than 1. Therefore, ultimate bearing capacity will reduce. This is what you should know. And very, very quickly, the equation for RW1 lies here. This is when the water table rises to a level above the base of the foundation and up to the ground surface. This length from the ground surface till the top of the water table we call as ZW1, and RW1 is given by this equation, wherein this is ZW1, and then you have D, where D is the depth of the foundation. So when the water table is above the base up to the top of the ground, water table can be either at the ground surface or at the base or anywhere in between. Please note, in geotechnical engineering, worst situation is due to the presence of water, or sometimes presence or absence of water. So the worst situation here will be when the water is up to the top of the ground. In that case, ZW1 will become 0. And check what happens to RW1. When ZW1 is 0, RW1 will be 0.5. So remember, when the water table is near the surface, RW1 will be 0.5. Now, let us talk about RW2. RW2 is considered in the third term. It is when the groundwater table is between the top bottom of the foundation and below that up to width b. So whenever the groundwater table is, let us say, at the ground surface or above the bottom of the foundation, automatically ZW2 will be 0. And when ZW2 is 0, RW2 will become 0.5. So friends, you should know, whenever the groundwater table is at the surface, you have the worst situation. RW1 and RW2 will both be 0.5. On the other hand, whenever groundwater table is at great depth below the base of the foundation, both RW1 and RW2 will be 1. Now, going back to the equation, when the second term and third term reduce to 0.5, reduced by 0.5, automatically QF will be reduced. And in sandy soil, cohesion C is 0. Therefore, QF quite likely will be equal to 50% of QF when the water table is at great depth. So, we should always remember that the presence of groundwater table is to reduce the bearing capacity. Now, let's go back to the question here. While designing a shallow footing in sandy soil, monsoon season is considered for critical design. Naturally, during monsoon season, groundwater table is likely to rise up. And in the worst situation, it will rise up to the ground surface. Otherwise, also, it is considered as the critical design in terms of bearing capacity. Therefore, the answer to this is yes. So that's what I have tried to say. Both RW1 and RW2 in the worst situation will be 0.5. Therefore, QF is likely to reduce to 50% of QF when groundwater table effect is not there. Therefore, above statement is true. So, once you know this is true, you go back to the question. Please note here, you have to read all the statements. P is true, you go here. Only in two of these, P is true. Okay? Therefore, the answer to this is either A or C. You can simply forget B and D. So, either A or C, for which you need some more information. Maybe one more. If you check, you should be able to get. So, let me go forward. I now try to consider quicksand condition. I do not know whether Professor Chetan is going to touch on this aspect. And I take this quicksand condition because, you see in the question R, it says that in a sandy sea beach, okay, in sea beach, mostly you see sand. Quicksand condition can happen many a times. You keep your feet Suddenly it appears on the sea beach, suddenly it appears that your feet are going down. So quicksand condition can arise only if critical hydraulic gradient exceeds the existing hydraulic gradient. So I go back to my discussion on quicksand condition, and please note that quicksand condition is not the type of sand. It is a condition, it is a state in which you have an upward seepage force which is acting upwards that balances the downward weight of the soil. So when downward weight of the soil, which actually gives the effective stress, is balanced by the upward seepage flow or pore water force, effective stress is going to reduce, and in the worst situation, it's going to become zero. That's when you say that quicksand condition has occurred. Why? Effective stress in soil is zero. It has no strength, no stiffness. You keep your feet on it, your feet will go inside. Even a small weight, even a pen, you keep there, it will not to take it its load. Soil is behaving like a fluid now. So please note, quicksand condition is not the type of sand. It's a phenomenon when effective stress in the soil reduces to zero. It's because of the upward flow of the seepage water flowing upwards. And when this equals the downward force, the effective stress will become zero. So people always are advised, and in case you are situated, you are forced in a quicksand condition, it's very difficult for you to come out, because the quicksand or the soil in quicksand condition will simply make you punch into the ground or just go deep into the ground, because your weight is good enough to take you down. So I have just considered a hypothetical case in the laboratory where, let us say, something like, permeability test. You have a soil here, okay, in a tank, and there is a tank containing water. When will the seepage happen? When this head is much, much more, water seeps from below upwards. So the effective stress in the soil is equal to effective stress, let us say at this level, is equal to sigma dash, which is gamma sat minus gamma W into Z, which is known, where gamma sat is the saturated density, gamma W is the unit weight of soil, or in general, that's equal to gamma sub into Z. And there is also seepage force. And this seepage force, when it becomes equal to effective stress, you have quicksand condition. So when the seepage force is equal to gamma sub into Z, you have the quicksand condition. Very easily, we can find out I critical. What is I critical? It is hydraulic gradient in the critical state when the system is in quicksand condition. In general, hydraulic gradient is H by L. So, friends, you should know that when hydraulic gradient reaches the critical value, automatically the soil is in quicksand condition. I just want you to see, people may ask, what is the difference or what is the relationship between quicksand condition and liquefaction? The relation is that both of them cause effective stress equal to zero, and both of them will reduce the strength and stiffness of soil very quickly. Liquefaction happens because of earthquake. Quicksand is always because of the seepage, and seepage is upward seepage. In liquefaction, it is the excess pore water pressure which is going to bring the effective stress zero to zero, whereas in quicksand condition, it is the upward flow of water which is going to make the effective stress zero. So liquefaction happens because of earthquake, therefore dynamic loading, dynamic condition. Whereas quicksand condition does not require any dynamic force. It is simply the static state. So in liquefaction, pore water pressure will be equal to total pressure, whereas in case of quicksand, seepage pressure will be equal to total pressure. But in both the cases, effective stress in the soil will reduce to zero. So going back to the question was, in a sandy sea beach, quicksand condition can arise only if the critical hydraulic gradient exceeds the existing hydraulic gradient. So whatever I explain now will indicate that quicksand condition can happen when existing hydraulic gradient becomes equal to or greater than critical gradient. So the question here is, if critical hydraulic gradient exceeds existing hydraulic gradient. No. Question should be existing hydraulic gradient exceeds critical gradient. Therefore, the statement is false. Since the statement is false, I go back here. P is true, R is false. So only in A and C P is true, R is false only in A. Therefore, the answer to this quiz question should be A. Anyway, you can get the confirmation with respect to Q and S, and that you can do, at a later stage if you have enough time. Let me go further. I talked to you about the different types of foundations, shallow and deep. Shallow foundations are preferred, and in this, isolated footing is what is preferred. Why? Because it costs less. You don't require sophisticated equipments. You can do the work faster. You don't require too much expertise to the engineer or the labor force. Therefore, the isolated footing is preferred. But not always you can go for isolated footing. Sometimes you may have to go for combined footing. When will you go for combined footing? Most important reason is when one of the columns is at the edge of the property line. You can't extend the foundation beyond the edge of the column. The other important reason can be the two columns are heavily loaded and they're close by. Therefore, if you try to provide isolated footing, they overlap. And hence, it is not acceptable. So, whenever the columns are heavily loaded, whenever spacing between them is less, and whenever SBC of the soil is low, you are forced to go for a higher order foundation, and combined footing is a higher order foundation. Interestingly, when the column next to the property line is heavy, the only option you have is to go for trapezoidal combined footing. So this is a case in which you have a trapezoidal combined footing in which P1 is having a load of 2,000 kilonewtons and P2 is having a load of 1,500 kilonewtons. All dimensions are given and you need to find out the length of the combined footing. So the width at the higher end A is given by 5 meters, at the smaller end B is given by 1.5 meters. Spacing between the columns is given as 5. And please note one most important concept which we adopt when we design a combined footing is, if possible, keep the upward pressure distribution, upward soil pressure uniform at each and every point. For that to happen, you try to see that the centroid of the area of the trapezium coincides with the CG of the loads. So you need to see that CG of the loads and the centroid, they coincide, they match. Let us try to find the CG of the loads. No difficulty. You have two columns at their centers, which are spaced, the two columns are spaced at 5 meters center to center. You have the load 2000 kilonewton on one side, in this case left side, and 1500 kilonewton on the other side, the right side. Therefore, from the edge of the footing, from the edge of the footing, the distance of the CG is fixed by the formula which I have given here. So the formula is, 0.25 is the width of the column, and then 1500 into 5 by 3500. Further, the centroid of trapezium, if I say that the left side is A, the right side is B, is simply given by the formula A plus 2B by L, into L divided by A plus B by 3, or A plus 2 by A plus B into L by 3. So equate these two, because these two should match. Equate these two and you will get L is equal to 5.83 meters. So the question here, the at the bottom, it says that if the stress beneath the footing is uniform, the length of the combined footing L in meters will be rounded off to two decimal places. So when it is rounded off to two decimal places, it is 5.83 meters. So friends, proportioning the foundation is very essential. We tried one with respect to mat foundation in the previous class. So proportioning the trapezoidal footing, strap footing, strip footing, or mat foundation will be very much required. Also, proportioning of isolated footing also will be a necessity. Please do practice that as much as possible. Let me go further. Look at the question here. I don't read it fully, but I want to tell you that this question is on settlement. I always tell people that settlement is one more area which we have to be very conversant with. In classes, I give classical examples of two settlements. One settlement is Mexico City, clay in Mexico City. It's soft clay which runs for a thickness of more than 40-50 meters, saturated soft clay. And whenever you load, because Mexico is a very populated city with many tall structures, whenever you load heavily, naturally under the load, consolidation settlement happens, therefore the settlement happens. In some cases, settlement can be of the order of 1 meter in 1 year, which means you build a 10-storied building today, maybe 4 years later it will become 9-story. So that's the kind of settlement which you see in Mexico City, Mexico clay, and you just cannot allow that to happen. There is always a permissible limit. When settlement exceeds like this, it can cause a lot of functional problems. Sometimes you may see water main going below sewage main, and several things may happen. Your road may be at a higher level compared to the buildings. Lot of confusions. The other important problem which I always talk about is Leaning Tower of Pisa. We know that whenever we talk about Leaning Tower of Pisa, we always know that it is tilted. And that tilt is because of the differential settlement. One end, the south end, is tilted much more to a level equal to 3.2 meters, or settled to a level equal to 3.2 meters compared to the north end, which has experienced settlement of the order of 1.6 meters. So in a span of 20 meters in the foundation, ring foundation, the differential settlement is of the order of 1.6 meters, which means, the building, the tower is tilted by almost about 4 to 5 degrees. And you have a problem of differential settlement which need to be addressed. So friends, settlement plays an important role and we need to work on that. So this question is about settlement. So we'll have a very brief theory and then go ahead. This question also, which came in the previous question paper, is on settlement. So we'll tackle this little later. So one thing you should know is that settlement is the vertically downward movement of the new building which you build with time. And this vertically downward movement happens in different rates under different situations and in different soils. So always remember that it has three components. One is elastic settlement, the other one is consolidation settlement, and the last one is creep, which may not happen in all the soils. It happens only in organic soils and very vulnerable soils. So most important are elastic and consolidation settlement. And consolidation settlement happens in clayey soils, which is a significant contributor for the settlement. On the other hand, elastic settlement happens in all soils. Therefore, you need to take this into account in every soil, but the effect is much less compared to consolidation settlement. So you can see here, this is the ground surface. Settlement happens downwards, and this is with time. The focus is with time. And soil is a peculiar material. Sometimes it can expand also. But initially, the settlement will be gradual for a short duration of time. And after that, in some soils, the settlement can or may increase enormously, which is due to the effect of consolidation. Please remember, total settlement has three components: immediate or elastic settlement, consolidation settlement, and secondary or creep settlement. For most practical cases, we can neglect secondary or creep settlement. And immediate settlement, as I said earlier, happens in all types of soils. It is due to the elastic settlement. And it occurs immediately after the load is applied. And it depends on the rigidity of the soil, the size and shape of the foundation, and some of the elastic properties of foundation. So it's given by the formula which is shown here. I'll not go deep into it. Okay. So it's given by the elastic properties of soil E and mu, and Q is the surcharge load, and B is the width of foundation. I rho, also called influence factor, is the property or value which depends upon how rigid the foundation is and what is the shape of the foundation. Let's now move on to consolidation settlement. And it is due to the process of consolidation. I don't have to explain in detail because my colleague will be talking about this. Remember, consolidation is due to the process of the removal of water from the soil mass. And this removal happens because of the extra load which we apply. And many a times, people confuse with compaction. So I thought I'll very briefly explain the distinction between the two. Please note that you have a soil mass, and if it is a three-phase system having some amount of air, water, and solids, when you apply some force, especially a dynamic force like an impact, quickly air in the soil mass gets expelled, and when air goes out, volume decreases. And this phenomena is called compaction. So compaction is generally man-made, and you do compaction because you want to increase the density of the soil. So it can happen in a soil which is partially saturated, which has some amount of air. On the other hand, consolidation happens in a soil which is fully saturated, and it is because of the removal of water. And removal of air is easy, quick. Removal of water takes a long time. So consolidation process is a long time process. And here also it is the decrease in the volume of the soil because of expulsion of water. Therefore, I want you to list or understand the distinctions between compaction and consolidation. Remember, compaction is man-made, consolidation is natural. Of course, artificially you can increase the consolidation, but in natural situation, consolidation is natural. Compaction is due to the expulsion of pore water. Compaction is a fast process. It can happen, within 2 to 3 seconds. to happen. The soil should always be hence, there should be no confusion between consolidation and compaction. One equation for consolidation, total consolidation, is given by SC, consolidation settlement, is equal to CC by 1 plus E naught. CC is the compression index and E naught is the initial void ratio of the soil, into H, the thickness of clayey soil. So consolidation happens only in clay. It doesn't happen in sand. Into log to base 10 of sigma naught dash plus delta sigma divided by sigma naught dash. Sigma naught dash is the effective overburden pressure. For convenience, we find out at the middle of the clay layer. And delta sigma is the extra pressure which is applied due to the new construction. So I now read this problem. A saturated compressible clay layer of thickness H is sandwiched between two sand layers as shown in the figure. So the figure is here. You have a saturated compressible clay layer, thickness is H. On top of it is sand, at the bottom of it is sand. That means, water, when it goes out here, it can go through the sand and go out, or it can go through the sand below and also go out, go back. Initially, the total vertical stress and pore water pressure at point P, which is located at the mid depth of clay layer, were 150 kPa and 25 kPa respectively. Therefore, the total vertical stress is 150 kilonewton per meter square. Pore water pressure is 25 kilonewton per meter. Construction of the building caused the additional total vertical stress of 100 kPa, 100 kilonewton per meter squared at P. Now, when the vertical stress reaches 175 kPa, what happens to consolidation in clay layer? So this is what you need to calculate. And this is clay which is sandwiched between these two sand. Okay, the thickness of clay layer is H. I have this equation for settlement, consolidation settlement. Before the construction, at the middle of the clay layer, sigma naught total stress is given by 150 kilonewton per meter squared, and pore water pressure is 25 kilonewton per meter squared. Therefore, effective stress sigma naught dash is sigma naught minus U, that is 125 kilonewton per meter squared. After full construction, delta sigma, in that is the pressure due to the increase in the pressure due to the structure, is given as 100 kilopascals. Therefore, if I find consolidation settlement after the completion of the construction completely, K is say it's equal to CC over 1 plus E naught into H. CC, E naught, H are constants for a given condition. Therefore, I just called all of them as K into log to base 10 of sigma naught dash is 125 and delta sigma is 100. Therefore, 225 by 125, and S1 settlement when complete construction is over is given by K into log to base 10 of 225 by 125. On the other hand, when the construction is partial, that's when effective stress plus the extra pressure due to the construction become equal to 175. S2 is equal to same K. So the values of CC, E naught, H are constant. Therefore, S2 is equal to K into log to base 10 of 175 by 125. Considering that percentage consolidation now, because the pressure now is less, is S2 by S1 into 100, which is equal to 57.2%. So the answer to the question here is that the percentage of consolidation in clay layer at P is 57.2%. This is what you people will have to remember. You have another question here. A raft foundation of 30 meter by 25 meter is proposed to be constructed at a depth of 8 meters in a sandy layer. So it is in sand. A 25-meter thick saturated clay layer exists 2 meters below the base of the raft. Below the clay layer, a dense sand exists. A 25 thick undisturbed sample is taken for laboratory testing from the mid depth of the clay layer and tested in the laboratory odometer under double drainage condition. It was found that the soil sample has undergone 50% consolidation settlement in 10 minutes. The time taken for 25% consolidation settlement in the field of the raft foundation is dash. So remember, this is quite tricky, and I believe my colleague Professor Chetan may deal with it. However, because it is acting in the settlement, as in settlement side, let me try to solve this problem. In the field, you have 8 meters of sand. Below this, you have 25 meters of clay. Below this, you again have sand. And the raft foundation is provided up to a depth about 2 meters above the clay layer. So about 6 meters is the depth of excavation. And therefore, if clay here consolidates, water can go out from top as well as in the bottom. So it is having double drainage system. And in the laboratory, you have only 25 thick clay layer. And usually you will have double drainage because you have porous stone at top as well as bottom. Therefore, you have double drainage. So both are double drainage. Therefore, in the field, it is 25,000 by 2. So 12,500. And in the laboratory, it is 25 by 2. That is 12.5. Both in millimeters. You should know that when the degree of consolidation is same in lab and field, then the time taken is directly proportional to drainage path squared. It is mentioned that in the laboratory, degree of consolidation equal to 50%. For that, time taken is given. But in the field, you want it at 25% degree of consolidation. So first thing you need to do is maintain consistency between field and lab. Maintain degree of consolidation to be same between field and laboratory. Therefore, try to find degree of consolidation at 25%. So you know that the equation for degree of consolidation less than equal to 60% is time factor TV equal to pi by 4 into U by 100 squared. So when TV you want for 25% degree of consolidation, it's given by pi by 4 into 25 by 100 squared, that is 0.0491. And TV for 50% consolidation, you use the same formula is given by 0.196. Therefore, time taken in laboratory for achieving 25% degree of consolidation will be obtained by this equation by a simple common ratio, and you find that this value is 2.5 minutes, much less than 10 minutes, because degree of consolidation is 25%, not 50%. So it is 2.5 minutes in the laboratory. So what next? You need to find out in the field how much time it takes. So you know the relation time taken in the field by time taken in the laboratory will be equal to drainage path in the field by drainage path in the laboratory to the power 2. So time taken in the field is equal to time taken in the laboratory multiplied by drainage path in the field by that in the laboratory whole square. That is 2.5 multiplied by 12500 by 12.5 whole square. So that amounts to 2.5 followed by 60 or into 10 to the power 6 minutes. You convert that to number of days by dividing by 24 hours and then 60 minutes. So number of days is 17.1736 point something days, but it is said that you have to maintain rounded off to the nearest integer, therefore 1736 days. That's the answer I have to give. Very quickly, we go to pile foundation, and there are a few problems which we have to address with respect to pile foundation, and these are the problems which are given in the previous GATE 2022 question paper. I don't have to mention to you that pile foundation is a popular deep foundation. It is in pile foundation that the depth of foundation will be much, much higher than the width of the foundation. It is in pile foundation you consider the presence of soil in the neighborhood on either side, and pile foundation becomes essential when the structure is heavy and when the soil near the surface is poor or weak or less strong. So you should know that there are two important ways pile foundation is constructed. One is board pile, which is done for smaller heights, smaller depths. You make a borehole first and then fill up concrete and steel. On the other hand, you also have driven pile in which you have a precast pile, which you nail into the ground just like you put a nail into the wall. Nail into the wall is put horizontally, but in this case, you put the nail or driven pile into the ground vertically. So the bottom has sharp edge. At the top, you have a head and you hammer from the top. And you don't want the pile to be damaged, therefore, you create that head. Remember, there are different classifications. Two major classifications are a pile which is socketed into the ground, in which case, whatever total load is there, that is shared at the base only, that is taken at the base only. The soil in the neighborhood is weak or it may be even offshore. So entire load is borne at the base. On the other hand, you have a floating pile, which is also called friction pile, in which the load is taken along the skin of the pile only. Not much load is carried at the bottom. It's very negligible. So this is what is floating pile or friction pile. So in a pile, the total capacity in general is shared by a frictional pile component and then the end bearing or tip base resistance. In special cases, you may have a pile which has only end bearing with skin frictional component 0, or you may have a pile where the end bearing component is very less compared to the skin frictional component. So in weak soil, the capacity of load carrying near the surface is very much reduced. So P is equal to P1 plus P2. P1 is the skin frictional component, P2 is the tip or base. So you should remember that total load carried will be partly as the skin friction along the surface and as the end bearing at the tip or at the base. So whenever a load is applied, initially load is taken by the top surface and gradually it is influenced, it is taken till the bottom. So usually the load resisted at the top is much more compared to at the bottom, and slowly the load is also transferred to the base. This is how the load transfer takes place, especially the skin friction will not happen immediately. It should be mobilized, and in a very stiff soil mobilization is less. On the other hand, in soft soil, mobilization is relatively higher. So, friends, therefore, total load carrying capacity is divided into two parts. One part taken as skin friction, and another part taken as the base. So, you have the pile capacity, which is given by skin frictional component and end bearing component, and hence, small q as is the stiffness or stress for the surface into area of the surface, and qp is the load carrying capacity at the base multiplied by ap. And in a purely cohesive soil, QS is equal to alpha into Cu. Alpha is the shear mobilized, and QP at the base is equal to Nc into Cu. All other terms, Nq, N gamma, will vanish because phi is very low. As I said, shear mobilization is more in a soil which is less stiff, and less in a soil which is more stiff. It usually ranges from zero point 0.3, zero point 0.4 to around zero point 0.8 or zero point 0.9. So let us take this problem, complete this. You have a square concrete pile, 10 meters long, square. It is driven into the deep layer of uniform homogeneous clay. Average unconfined compressive strength, which is determined from the laboratory test on undisturbed samples, is 100 kilopascals. If the ultimate compressive load is 632 kilonewtons, required width of the pile, it's a square pile, is given by how much? Please take NC equal to 9, alpha equal to, that is addition factor, alpha equal to 0.7. So you have a pile here in a clay soil. The length of embedment is 10 meters. In cross section, it looks like this. So width is B, and this is the value which you need to find out. So PU, ultimate load, is 632. It's given that soil has a unconfined compression strength of 100. Therefore, Cu is equal to 50 kilopascal and L is 10 meters. Pu is equal to, that is the ultimate load carried, is equal to load carried at the base plus load carried due to the frictional component. That's equal to the resistance or stress multiplied by area at the base. Again, resistance or stress multiplied by area to skin friction. At the base, stress is equal to alpha into Cu multiplied by the area. I'm sorry. At the base, it is Cu into Nc multiplied by area. And at the surface, it is alpha into Cu multiplied by corresponding area. So if it is a square pile, AB is equal to B squared. Okay. AF is equal to 4BL. And hence, I substitute this value and I get a quadratic equation in terms of B. Solve this and you get P is equal to 0.4 meter. So this is all the solution, which is very simple. Now that we have crossed the time, I'm going to close this, and I just want to tell you that you can find the capacity of the files by dynamic formula. Two important theories. One is the engineering news formula, which is very simple, and the other one is Hiley's formula, which is given in our IS code, IS 2911. So, dynamic formula, the biggest advantage is whenever you have a driven pile, you are anyway going to drive the pile using dynamic force, therefore, you can find. So, there are a few advantages with this, which we may discuss at a future time. I'm going to close my lecture at this point of time, and I'll be extremely happy to answer your questions. Please do go through the YouTube of our institution. And if you have questions, you can mail it to me, you can pass it on by any means. You can also refer to my phone number and talk to me, and I'll be pleased to answer. I want you people to practice, do your problem solving as quickly as possible. And I stop at this stage, wishing all of you a good time and good preparation for GATE 2023. And I want you people to succeed in that. Thank you very much. I'll meet again, in a couple of days. Good luck to all of you.